So moving along, okay, let's just remind ourselves what the various trig functions are by definition. So in the unit circle, if I mark off an angle of theta, I get an x and a y coordinate. So this is the unit circle, the radius is 1. By definition, x is the cosine of the angle, and y is the sine of the angle. Then we add in things like tangent is y over x, cotangent is x over y, secant is 1 over cosecant is 1 over y. So in quadrant 1, x and y are both positive, which means the sine is positive, the cosine is positive, but since sine is positive, so is cosecant. Observe, since cosecant is just 1 over sine, if one of them is positive, the other one is. That's why they just get the same column. Similarly, since secant is 1 over cosine, if one of them is positive, so is the other, so they're just getting the same column. And since cotangent is just 1 over tangent, if one of them is positive, so is the other, so they get the same column. So in quadrant 1, x and y are both positive, which means all of these things are going to be positive. Now, in quadrant 2, x is negative and y is positive. Since y is still positive, sine and cosecant are still positive, but now cosine and secant are negative. And my ratios x over y, since one of them is positive and one of them is negative, those ratios are going to be negative. Okay, in quadrant 3, both coordinates are negative. So now my sine and my cosecant are negative because y is negative. My cosine and my secant are negative because x is negative, but the ratios have gone back to being positive. X over y is going to be positive again, as will y over x. And in quadrant 4, y is negative, but x is positive, which means y is negative, so therefore sine and cosecant are negative. X is positive, therefore so are cosine and secant. And since I have a single negative and a single positive, the ratios will be negative. So this is just a little chart to remember. In different quadrants, the various trig functions are guaranteed to be positive or negative. Okay, so here's a summary of everything on the previous page. Again, since the way this is drawn here, by the way, is this is just the x comma y coordinate. They're both positive in quadrant 1, but in quadrant 2, x is negative and y is positive, etc. Okay, so this is all redundant with the previous chart, but it might just help you remember it visually. Okay, so sine and cosecant, looking at the charts on the right, sine and cosecant are always the same SIGN sign. They're either both positive or they're both negative. And they're positive when y is positive, and they're negative when y is negative. Cosine and secant are positive or negative according to whether x was positive or negative. Tangent and cotangent do this ratio thing. So either both positive or both negative makes the ratio positive. But if one is positive and one is negative, the ratio is negative. So suppose sine of theta is negative and cosine of theta is positive. What quadrant does that angle live in? So sine of theta is negative. Okay, that tells me that the y coordinate is negative. The cosine of theta is positive. That tells me the x coordinate is positive. The only quadrant where y is negative and x is positive is quadrant 4. Okay, we've already kind of used this. The cosecant is 1 over the y coordinate, but the y coordinate was just sine. So cosecant is 1 over sine. Secant is 1 over the x coordinate, but the x coordinate was cosine, so secant is 1 over cosine. And cotangent was x over y, which is the reciprocal of y over x, which was tangent. So cotangent is 1 over tangent. Okay, we can also express tangent as y over x, that's sine over cosine. These are all things the book is just introducing now. I kind of put them up on earlier slides anyway. And the point being that all of these other functions can be defined in terms of sine and cosine. So sine and cosine are the ones you really want to understand the best. So suppose sine of theta is root 2 over 2, and cosine of theta is 5 root 2 over 2, which it can't be. So I am suspecting this is a typo and there's not supposed to be a 5 there. Incidentally, how do I know that cosine of theta can't be 5 root 2 over 2? So root 2 is approximately 1.4. So root 2 over 2 is approximately 0.7. But I have 5 root 2 over 2. That's 5 times as big. This is going to be about 3.5. But what's the biggest cosine can ever be? Cosine can't possibly be bigger than 1. That's how I know there's an error here. I suspect the 5 just wasn't supposed to be there. And, well, all right. I'm going to go ahead and fix this problem as we go because it doesn't make any sense. So here, the tangent would actually have to be 1. Okay. If sine is root 2 over 2 and cosine is root 2 over 2, well then, the tangent would be 1. The cosine would be 1 over the sine, and 1 over root 2 over 2 is just 2 over root 2, which does simplify to root 2. Secant would be 1 over the same thing, which would simplify to the same thing. And cotangent would be 1 over the tangent, but the tangent was just 1, and that simplifies down to 1. So I'm actually going to do a similar problem here to make up for the fact that the book one had an error in it. So suppose sine of theta is equal to, let's call it a third, and the cosine of theta is equal to 2 times the square root of 2 over 3, but it's negative. Okay, this is a legitimate pair of points that I can pick. So then, what's tangent theta? Well, tangent theta is sine over cosine, which is 1/3 over negative 2 root 2 over 3. The over 3's cancel, and I get negative 1 over 2 root 2. I would leave it like this if you really don't want radicals in the denominator. You call this negative root 2 over 4. This immediately tells me what's cotangent of theta. Well, cotangent of theta is just 1 over tangent of theta. So here was my expression for tangent. So if I reciprocate it, I just get negative 2 root 2 over 1, which is just negative 2 root 2. Okay. What else do we need? Secant theta. Secant theta is 1 over cosine theta. Since cosine theta was negative 2 root 2 over 3, this is just negative 3 over 2 root 2. I'm fine leaving it like this if you really don't like radicals in the denominator. Call it negative 3 root 2 over 4. And finally, the cosecant of theta is just 1 over the sine of theta. Sine of theta was given to be a third, so 1 over that is exactly 3. Okay, so hopefully that makes up for the error in the book's version on the previous slide. Now we have this fundamental identity, sine squared theta plus cos squared theta equals 1. And then these associated identities. Now, what are labeled as equations 6 and 7 are not really new formulas. They're actually the same one as number 5. So let's understand why number 5 is true. And then we'll understand how 6 and 7 come from it. So we're on this unit circle. What's the equation of this circle? Since the radius is 1 and the center is at 0, 0, the equation of this is just x minus 0 squared plus y minus 0 squared equals the radius squared. Simplifies down to a nice x squared plus y squared equals 1. This is true for any point on the circle. So if I mark off any angle I want, the coordinates of this point, x is cosine theta, y is sine theta, and I just plug those in here and we get exactly this. So this is just replacing y with sine theta and x with cos theta in the generic equation of the unit circle, because the unit circle was used to define sine theta. Okay, so that's why this is true. So now imagine you take this expression, sine squared theta. By the way, sine squared theta really should be written as sine of theta squared plus cos of theta squared equals 1. It's just super common notation to put the exponent in front of the sine function. This means take the number sine of theta and then square it. It doesn't somehow represent square the letter n or anything like that. It means take the sine of theta and then square it. So we have sine squared theta plus cos squared theta equals 1. Now what I'm going to do is I'm going to divide both sides by cos squared theta. As long as I'm not dividing by 0, this is okay. Now on the left, I'm going to split this up as sine of theta squared over cos of theta squared plus cos of theta squared over cos of theta squared. And on the right, we get 1 over cos of theta squared. Well, this can be rewritten as sine theta over cos theta squared plus 1 equals 1 over cosine of theta squared. But what's sine over cosine? That's tangent. So this is tan squared theta plus 1 equals, what's 1 over cosine theta? Secant squared theta, because I squared it. So if you just take this Pythagorean identity, it's called the Pythagorean identity, by the way, because in the unit circle, if I mark off any radius, I know this is 1. This is x, this is y of this point x comma y. So the Pythagorean theorem exactly gives me x squared plus y squared equals 1. And then we use x equals cosine theta, y equals sine theta. Okay, so once we know this expression, dividing everything by cosine squared got me here. But if I instead divide everything by sine squared over sine squared gives me a 1. 1 over sine squared is cosecant squared, and cosine squared over sine squared is cotangent squared. So it's really the same formula divided by sine squared. So don't worry about trying to remember all 3 of these. Definitely remember this one. And then just make a mental note. I can divide by cos squared to get this, or I could divide by sine squared to get this. But really the only one I have to remember is the fundamental Pythagorean identity, and that's just x squared plus y squared equals 1. Okay. So here is a nice summary of all of these reciprocal and Pythagorean identities in one place. Tangent is just sine over cosine. Cotangent is the reciprocal of that. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. Sine squared theta plus cos squared theta equals 1. I can't emphasize enough how fundamental that is. Okay. And if you divide by cos squared theta, you get tan squared theta plus 1 equals secant squared theta. And if you divide by sine squared theta, you get cotangent squared theta plus 1 equals cosecant squared theta. Nothing new on this slide, just a summary. Okay. So let's use all that to find the following. Find the exact value of each expression without using a calculator. Okay, so cotangent of 40 degrees minus cosecant of 40 degrees over secant of 40 degrees. Spoiler alert, don't try to compute cotangent of 40 degrees. We don't know what it is exactly. Similarly, cosine or cosecant of pi over 16, we don't have an exact value for, but we don't need them, okay? Because cotangent is just cosine over sine, cosecant is 1 over sine, and secant is 1 over cosine. So on that right term, I have a fraction over a fraction, which simplifies down to just that. So whatever the cosine and sine of 40 degrees are, and I don't know exactly what they are, but I know for certain that cosine 40 over sine 40 minus cosine 40 over sine 40 is guaranteed to be 0. So even though I couldn't determine the terms individually, I definitely know the result is 0. So similarly, let's take a look at part B. So cosecant is 1 over sine. So 1 over cosecant squared is the same thing as sine squared. So now I have sine squared pi over 16 plus cos squared pi over 16. And even though I don't know what those are individually, I know for any angle, sine squared of that angle plus cos squared of that angle is always 1. Even though I don't know what they are, I know that when I take sine squared plus cos squared of the same angle, I'm always going to get out 1. Okay, so we'll stop there. There are some examples given as like exercises in the book that are similar to this, like simplify the following, and they look terrible. Just remember your fundamental, I'll flip back to the slide that happened. Just remember these fundamental identities and use them to simplify things that otherwise you wouldn't be able to do. So after this, we'll come in for the last video in this section, where we're going to just start working through a bunch of problems that are similar to exam problems that we give out of this section.